the width of the Fourier transform controls the width, the overall width of your function. The larger, the wider is the Fourier transform, for example, quantified by full width at half maximum. The wider is the Fourier transform, the narrower is your function. You're packing more and more harmonics, more and more frequency components. And so there's a narrower and narrower region of space or time, depending on what the meaning of the axis is. There's a narrower and narrower region of that x-axis where all of those frequency components would agree. So that makes the signal narrower. On the other hand, if the Fourier transform is very, very narrow, it means it's basically, if you squint your eye at it, you basically have just one or a handful frequency components. Okay, and then, well, if it's one frequency component, you get a pure sine wave, which has infinite width, right? It goes from minus infinity to plus infinity. And if you have a handful of other frequency components, it modulates that sine wave. So there's an inverse relationship between the width of the Fourier transform and the width of the function. Moreover, the peak of the Fourier transform gives you the wave number or the wavelength, or again, in time domain, it would be the angular frequency or the period of the most loud frequency component, the most loud, the most dominant harmonic. And that's really what those wiggles are inside the function, right? The quasi sine wave that makes up your wave packet is that dominant component. Now, it's not a pure sine wave because you have all the other harmonics that eventually make the wave packet go to zero. That's their role. But the dominant, the loudest term, basically gives that those wiggles. Right. So 58, you should be able to answer part A and part B. One thing that I think I should talk about, so regarding problem 58, and I think maybe also 59, the meaning, the physical meaning of A of k. Just as the square of the magnitude of the wave function in quantum mechanics has the meaning of probability distribution of position measurement outcomes, so is the square of the magnitude of the Fourier transform has the meaning of probability of momentum measurement outcomes. So for example, if your A of k looks like this, some kind of a thing. So this is, let's say, A squared. It's a function of k, right? So what's the most likely value of momentum? So this is most likely momentum result is, remember P equals h bar k, so this is k naught is h bar times k naught. Okay. So remember, there's a relationship, de Broglie relationship. So you can even maybe express this in terms of momentum. You just rescale the x-axis and express it in terms of t, right? So this would be, so maybe p naught, right? So you could rescale the x-axis. So for example, if k naught is pi per nanometer, then p naught would be h bar times pi per nanometer. Now, why that is, we would have to wait. But what does it mean? So let's say, let's go back to plane wave, right? Again, this is an example of a wave function. So you have a wave function that's a function of x and t given by something like this. Okay? This has a particular wave number. So this corresponds to a particle with momentum h bar k. Okay, let's say this is k naught and omega naught, h bar k naught. K naught being particular value of k. In this case, a measurement of momentum will always give h bar k naught. Okay, and a measurement position can give anything. Measurement of position can give anything. Now let's look at a different example. So this is example 2. Now let me erase this. So this would be a1 e to the I k1 x minus omega 1 t. And remember, we know how k's and omegas are related for a free particle, plus a2 e to the I k2x minus omega 2t. So this is the wave function, and its Fourier transform is just this. Okay, this is not a continuous Fourier transform. It only has 2 bars. Just like in your WaveLab example, we had discrete and then we had continuous. Later, we will see that a physical solution can only have continuous A's. So these examples, they're not actually physical. They're not physical because this wave function is not normalizable. But I'm sweeping that under the rug, right? So let's say we look at a wave function like that, because once we understand discrete, it's easy to go to continuous. So here's the Fourier transform. And to say that the Fourier transform squared gives probability, it means the following. Then a measurement of momentum can yield either h bar k1 with probability a1 squared, or h bar k2 with probability a2 squared. So I wanted to make this concrete. What does it mean to say that the square of the amplitude of the Fourier transform gives the probability distribution? Here's a simple example where your wave function is just made up of 2 harmonics. And then it turns out that these coefficients right here, they give the probability of obtaining either momentum h bar k1 or momentum h bar k2. I hope this is making things clearer. Now, I didn't really want to discuss it because, for one thing, I want to explain why that is. I'm not explaining why it has this meaning of probability. And second, I think your textbook also doesn't really talk about it, but I think it must maybe glance over this. So since you have problem 58, which requires you to know this, I thought, okay, I will just give you this information right now, even if it's a little bit sort of not following a purely sequential order. So now if I have a wave function made up of 3 harmonics, a measurement of momentum can give either h bar k1 or h bar k2 or h bar k3, respectively, with probability a1 or a2 or a3. Okay? We'll have a lot more to say about measurements and outcomes and statistics and averages and things like that. Like I said, we're building sort of layer by layer. But here's some information for you. It will allow you to do 58 more efficiently, or in fact, part C, you need this information.